Hello, welcome back to 14 Minesweeper variants. We've talked to the first 14 Minesweeper variants, so without further ado, let us go into the real fun part of the game, which is the combination levels, and also AND apparently. That's a new thing. But let's look at the combination levels first. Now, combined means that two random rules are combined. Not really random, it's more like one from each side is combined. A random one from the left and a random one from the right are combined. So for example, here we have two flowers and two modulo. Now the rules of flowers are that for each colored cell here that has a mine, that mine must be adjacent to exactly one other mine in a non-colored cell. So this cell, for example, is adjacent to exactly one mine. So this is valid. However, this mine on a colored cell is adjacent to two non-colored mines, so that's invalid. And there is no restriction on this kind of thing. So non-colored mines could be on their own, it could be adjacent to any number of mines. But colored has to be exactly one mine adjacent to it. Next, we also have modulo. Modulo basically means the number. The clue describes the number of mines mod 3. So it's the number basically you get when you divide it by mod 3. The remainder you get when you divide by 3. So this one, for example, is next to 7 mines, and 7 is congruent to 1 mod 3 because if you divide by 3, it's 6 plus the remainder of 1. So it's a 1. And so with those two rules, we're going to be playing this Minesweeper. Alright, so let's begin with possibly this 0-2 combination. This 2 must see 2 mod 3. And this 0 indicates that these 4 cells have a number of mines that is equal to 0 mod 3, congruent to 0 mod 3. So it could be 0 mines, it could be 3 mines. But either way, the 2, to ensure that it is a 2 mod 3, must have exactly 2 other mines. So there you go. This mine we can now use flower actually, because colored mines must have exactly 1 mine adjacent to it. So this can't be a mine. Now this 0 could not be a pure 0 because it already has a mine next to it. So it must be the next biggest, it must be the next smallest, which is exactly a 3, which is 0 mod 3. So those are both mines. And yes, and both of these mines must be adjacent to exactly 1 mine. So there you go. Orthogonally adjacent. Yeah, a common mistake that I make normally is assuming that a common mistake that I always make is that I don't mark this as a mine just because I assume that, I only really focus on this cell having more partners than 1, but having 0 partners is also not valid. Okay, well, either way, this 0 must not be a 3, indicating that there is 1 mine here. It could be anywhere here though, I'm pretty sure. Ooh, this 1. Okay, this 1 is either a 4 or a 7 because it already has 4 mines around it. However, it can't be a 7. If it was, you must have a mine here, here, and here. And well, this mine and this mine both fail. They all have mines, 2 mines next to them. So that means it must just be a 4. So these are all empty. This 1 indicates that there is 1 mine here because it can't be a 4 or greater. That would complete the 0, which would have 3 around it. Yeah, you can't have 6 around it because there's not enough space. So having 3 around it means that it's not a mine. And this 2 is just a pure 2 because the next number that is a 2 mod 3 is a 5, which there is not enough space for. So okay. Cool. Now this 0 over here. 0 already sees a mine, so it's either a 6 or a 5, or a 3, sorry. But I'm pretty sure it can't be a 6, because if it was, you'd have mines in all of these cells, and then that breaks the 2. It also, well, actually, yeah, it breaks this cell in terms of flower, so yeah, it can't be a 6, it's definitely just a 3. Should I draw a 3 here to show that's a 3? I should turn pane transparency off so you can see that, but whatever. Alright, so 3 mines total around here, and because there are 2 mines here, and we know that this has to be exactly 2 mines, that will complete the 3, and so this is not a mine. Therefore, this is a mine. Now this 0, well, can't be a 6 because there's not enough space, so it is a 3, and therefore it's complete. This 0, well, it can't be a 6, it can't be a 0 either, so it's a 3, which means that there's 1 mine here. However, by flower, it can't be on a colored cell, because this one would then be empty, which breaks this colored cell. So it must be here. There you go. And this 3 is basically complete, so those are both mines, and with no mines remaining, those are both empty. There you go. Okay. Well, that was fun. What, complete 10 levels in plus? Have I? Oh, I guess I completed some. No, I completed 1 here. And I completed 5 here. That's 10. I just got an achievement for completing 10 plus levels. But, okay. Oh my goodness, plus end. And then 2 hashtag. I don't know how hashtag works. I don't know how, because 2 hashtag is different from regular hashtag. Alright, next puzzle. Oh, geez. Oh no, bridge and area. Yeah, I heard that bridge and area is like a horrible combination, but we'll see how it goes. So the easier variant here is bridge, where you have 2 chains of mines going from left to right. And they must either connect horizontally or diagonally only. So vertical connections are not allowed. And you must form 2 chains, basically. 2 separate chains that cannot intersect either. Okay. So an implication of that is that if you notice every column, there are exactly 2 mines, and this is true for every board. Well, for 7 by 7 and larger, you get 3 chains. So every column is 3 mines. Yeah, so as you can see here, this chain doesn't even connect to each other, this chain doesn't even end, and this chain has vertical connections, which doesn't work. So yeah, that is the easier variant. This variant is significantly harder, I think, and states that each clue is equal to the sum of areas of mine regions around it. So this 7, for example, is a 7 because it's 5 plus 2. So it's an area of 5 plus an area of 2, so it's a 7. So this 5, for example, is touching an area of perhaps 1 and 4, or 2 and 3, or it's just touching an area of 5. That's possible as well. But in general, we want to form 2 bridges plus fulfill all the area requirements. Okay. Now I want to say that this can't be. It has to be a mine. Does it have to be a mine? Yeah, I think it has to actually. It has to be a mine, and the reason why is because suppose it was not a mine. There are a few ways to. Oh no, it could be a non-mine if you had something like this actually. That's very valid. This is a valid way of making a 2 work, and then you can form a bridge as well. I was like, if they were a contiguous group of mines that form 2, something like this wouldn't work because there's no end. Something like this wouldn't work because this would have to go to here and then you form a group of 3. But no, it is possible for you to have a mine here, here, and here, and then your chain goes this way. So this could be empty. Could also be a mine. If it was a mine, then what? Well, interestingly, if it was a mine, then this can't really be a mine, right? Because you do this and then that will isolate this cell, because yeah, you can't grow this region anymore. Huh. But if that happens, then this probably can't be a mine either. Oh, but it can, because it can grow. Ah. So there's some difference between this and this. It's not even diagonally symmetrical anymore, because your bridge is bridging from left to right and not in both directions. Oh, so this is plausible. So that could be a mine. Wow, okay. You know what? I was gonna say the 5 probably helps, but not entirely. We might have to think about this. I might have to think about this one, the 5. So suppose this was a mine, it would have to escape here. A couple interesting things to do with this though. You could merge and get a group of 4, that's plausible, and then this one goes out and this one goes out. And then, I don't know. So you could have a set of mines that kind of just look like this. That's valid. Oh, although, ooh, okay, no, I see. It's the 2 and the 5 together, because we know there have to be some mines here, or do there? Yes, there has to be some mines here, and there also have to be some mines here. For zeta 2 is very easy to justify why there has to be some mines here. Basically, you know, there has to be a mine here or there, basically. And so, yes. The 5 might be a little bit challenging. There could be a mine here. If there were a mine here, though, to fill your 5, well, it must grow, so there must be a mine there. So, in any case, there must be a mine in one of these places, and in one of these places. That feels very suspiciously like those are just the two ends of the bridge, right? Those are just two ends of the bridge, and you can't say two ends go together. So you can't have a situation that looks like this. Oh, because one of the ends have to be here. Oh, okay. That's fairly interesting. So what are we looking at then? Are we possibly looking at this, followed by this, followed by a group of 4? Maybe. I want to say, is this possibly a mine? Because if it was a mine, can't be hit by the 2, right? Can't be hit by whatever chain this is. Although that could happen. Well, could that happen? If this is a mine, I don't think this can be a mine either. Because if it was, then this would all just be false and then this mine would be isolated. So if that was a mine, then this is not. Which means this must be a mine. But now this is isolated. Oh, okay. I think that just means that this can't be a mine. Wow. That is crazy though. Okay, well, again, since we know that there has to be an end here, and that there are 2 mines in column E, we can then say that there is one mine here and one mine here. Well, either this is a mine. If this is a mine, then you'd have something like that. But if this was empty, then this has to be a mine. So either a mine here or a mine there. What about this? Could this be a mine? Well, it's very interesting that there's a 6 here, which is actually really large for bridge area. Because if you see here, the fact that they have to like sort of do this is kind of intriguing. As you can see here, it's a really pretty restricted. They have like large regions total. But I mean, that's not entirely true because the 6 could be of different sets. So it could be like 3 here plus 3 here. Although once again, this has a maximum size of 2. So 6 must have 4 more. And I'm sort of tempted to say the 4 has touched the 5, which means the 5 must have 1 more after that. And the reason why is because if there are 6 total, yeah, the 6 and 5 have to share, basically. And the reason why is if they don't share, then they would have 11 mines total, and there are only 10 mines total in this board, which is impossible. So 6 and 5 have to share mines. And I think because this is at most a 2, the 6 must touch at most 4 more. Which means what? Which means a 5 also touch 4 more from the 6? Not entirely sure. I mean, we know that this has to come from here or there, because these can't both be empty, otherwise the 2 is broken. So, I mean, could this be a mine? This could be a mine if it goes into here. Something like looks like this. That means that this can't be a mine, which means that. That's pretty interesting. Except now this can't be a mine. And the 5 is a bit weird. Because the 5 must just touch a region of 5. But this region will be 4. And therefore, the 5 needs to touch both the 4 and an extra 1, which it can't. So what that means is I'm pretty sure this can't be a mine. Now because this has a maximum size of 2, this must be a mine to increase the size touched by the 6. And therefore that can't be a mine. 5... Well, again, because this must be at least 4, I think. This must extend twice. 5 touches this already, which is already a size of 4. But because touching a mine here would not increase the... It wouldn't give 5 an extra 1. So this size can't be 4. This mine actually has to be a region size of 5. So this is a 1, which means that. Which means that. Oh, okay. Imagine if this was just a straight line of 5. It's possible, but... Is there any reason why it's not? Well, I guess this can't be a mine, because if it was, it can't connect to this, because this mine is already taking it. So this can't be a mine. Similarly for this can't take this mine, so that can't be a mine either, so it keeps growing. And does the logic hold? Yeah, this mine can't reach here. How about this mine though? It could do something like this. But I guess we know this isn't a mine. Yeah, there could be a mine here if it bridged up to this. So like, I think this is a valid setup because you have 5 here. But another valid setup could be something that looks like this, and then your upper chain goes like that. Oh, this 2 means that this can't be a mine because it can't grow. 4. Well, I mean, this has to keep going, and this has to be, well, it could be something like this because this does touch 4. Okay, well, once again, let us consider this scenario where this is a mine. If it was, then we know the 2 chains sort of converge here. This therefore can't be a mine, and therefore has to do something like this to make this chain. This breaks the 4, I'm pretty sure. Yeah, because wherever this grows next, you can't fulfill the 4. So I think what that means is this can't be a mine, and therefore this has to be a mine, which gives you just a bridge of 5. That's cool. 5 here is already touching 5, so these are both empty. 4 must touch small, which must grow even more. So there you go. I think that just solves everything. That's 2 chains. It is. Alright, there you go. Wow. Bridge area. This is definitely one of the tougher variant combos. But there you go. Okay, jeez. Let's keep going. Hey, doubles. That's fine. Yeah, is it F and M just now in the notes? Okay, fine. So this is triplet plus liar. Triplet indicates that mines cannot form 3 in a row vertically or horizontally, and non-mines cannot form 3 in a row vertically or horizontally. No diagonals in this one. And liar. Every liar is exactly 1 greater or 1 less than its actual value. So this 4, for example, if it was a liar, could actually mean a 3 or a 5. Every row and column has exactly 1 liar. So, for example, if this was a liar, then this would be telling the truth. Alright, so let's start this 4. I think this 4 has to be a liar, because if it was telling the truth, you have to put a mine in every of these cells, which would form a 3 in a row already. So this 4 is definitely lying, which means I can mark it as lying here. And now, because it can't be a 5, it must just be a 3. That means that this 2 is telling the truth though. This 2 is a 2. Oh right, by regular triplet, these are both mines because they can't have 3 non-mines in a row. 3 and 2 actually work very similar to a 2 and a 1, where because there are 2 mines in here, there has to be at least 1 mine in these 2 cells, which will complete the 2. So there will be no mine here, and because there's 1 mine here, there has to be a 3rd mine here to complete the 3. Now, this 4, by the same logic, can't be telling the truth, because if it was, you'd form a 3 in a row. So this 4 is lying. And this 4 must therefore be a 3, which can't occupy all 3 of these, so this must be a mine. Another way of thinking about it is that this can't form a 3 in a row, so there it is. This is empty. It's a 3, which is telling the truth. And 3s in this triplet are actually really special. They have a set, sort of... So if you've played tic-tac-toe before, you've seen that challenge where can you form a board with 6 mines in it, but none of them form a 3x3, a 3 in a row. And so this is sort of a similar idea, And the logic is that for this 3, it is looking at this board and cannot have 3 in rows. So what that means is that every row must have a mine in it, basically. You can't form 3 in a row without mines. And so your final square around the 3 has to sort of has to be like 1 mine per row and 1 mine per column. For that reason, you can mark this as non-mine. 5 could or could not be lying. But another interesting thing is that because there's 1 mine per row, none of these can be mines either. 4. Could 4 be lying? I'm not sure. We know that's a mine by a triplet. That's a mine by triplet. And because there's only 1 mine per row in this 3x3, that can be a mine, which gives us our final mine here and there. This 4 is definitely lying. And because there is 1 lie per row and per column, this 5 must also be lying, which means the last lie is here. Yep. 3 here is complete because it's telling the truth. 5 can't be a 6, so it must be a 4. Well, we already know that there's 1 mine here. This 3 is lying. But it could be a 2. Oh, this 2 is complete. This must be a mine so that you don't make 3 in a row. This must not be a mine. And how many mines do we have left? 2 mines remaining. This can't be a 2 then, because if it was a 2, then these are both non-mines. You don't have enough space to place the remaining 2 mines. So this must be a 4 with both mines here and here. And that leaves this to be a non-mine. There you go. Alright. Next up. H and D. Alright, we're going back to the nicer variants. So H means that mines must have horizontally adjacent partners. So every mine must have something to its left or to its right. And D is deviation. So clues don't talk about the 3x3 around them, talk about the 3x3 centered around the cell above it. So this one, yeah, looks at this set of tiles. Now, horizontal with 1 on the corner or on the side is very similar to, it acts the same way. So none of those can be mines, because if those were mines, then the 1 will be fulfilled, and therefore this causes an isolation of this mine. So it doesn't work, none of these are mines. 0, well 0 is done, 1 must be there, and 1 must have a partner, and this feels very wrong, but this 1 is actually looking above it. 1 looking above it implies what? I don't know, but this 1 actually works pretty similar to this one. You can't have a mine here or there, because then it will be isolated by non-mines, so none of those are mines. 0 means that happens. What? Oh! Yeah, I fell for it. This 0 is looking at this set. Oops. Of course. And so there's 1 mine in here. We've marked a lot of mines before, but I'm not sure. Well, there is 1 mine in here, which will fulfill this 1, so that can't be a mine. 4. Well, there's 1 mine here, so these 3 are all mines. This must have a partner, so that's a mine. This must have a partner, so that's a mine. Meaning that's not mine. This must have a partner, so it must have a mine here. This 1 is complete. And this can't be a mine because it will be isolated from a partner. And 4 mines remaining, so all those are mines. Nice. Very cool. That was easy because easy variants. Connected product. Alright, let's keep looking at the variant rules then. Connected. Connected means that each 4 connected mine region is a rectangle. So any connected region of mines orthogonally, so 4 connected means orthogonally connected, form a rectangle. So a rectangle here, a rectangle here. These don't count because they're not rectangles. And all mine regions are diagonally connected. So your regions must touch each other diagonally. And that's it. Product though. Okay, product is really tough. I have a full video, not analyzing but sort of working with product if you want to go and watch that. Clues represent the product of distances to the nearest 2 mines. So just a quick recap for this. Root 5, for example. This is a distance of 1 away from it. This is a distance of root 5 away from it by Pythagorean theorem. And therefore, the product of 1 and root 5 is root 5. Yeah, okay. So let's look at this root 2 first. No, that's not. This 2. This 2 is our either 2... oh, wait, hold on. Let me think about this. I was like, this 2 is either a 1 times 2 or a root 2 times root 2. And if it was a root 2 times root 2, you'd have something that looks like this. And none of those can be mines because those would be distance 1 away, which is less. Is that fine? I mean, it looks fine so far. This root 2, however, is a root 2 times 1. And it can only be a root 2 times 1 because no other pair will work. So it must have exactly one mine around it in this diamond. That kind of leads itself to this cell. Because if it was, it almost is isolated. The only way you could not isolate it is by putting a mine next to it to help save it out. Which sort of works, but that implies that none of those are mines. If this happens and that happens, I mean, you could still save it by doing things like this. But is there anything better? Oh, it's this 2. Because if this 2 saw a 1 away, saw a mine 1 away, it can't see anything else at 1 away, otherwise it would just say 1. It can't see anything else root 2 away either, because otherwise it would just say root 2, and that isolates it. So this can't be a mine. What is that? That's a root 10. Oh my goodness, a root 10, as we've seen here, is generally equivalent to root 2 times root 5. But root 10 can also be equivalent to 1 times root 10. And root 10 is in fact the distance you could have, because 10 is root 1 plus 9, which is 1 square plus 3 square. So a distance like this, that is root 10 away. That is root 10 away. So root 10, I'm going to try to derive this myself again. It's either 1 times root 10. So you either have a mine... Well, I mean 1 times root 10 is pretty tough though. Because a 1 times root 10 requires you to first have a mine here, but have no mine that is smaller than root 10 away. So because root 10 is here or there, basically none of these cells, none of those cells, in fact this cell can't have anything either. Right, because those are not more than root 10 away. And so all of these will be empty. And that pretty sure breaks the 2. Because the 2, it sees a root 2 there, but it can't see another root 2 to make 2. So I don't think this 10 is a 1 times root 10, I think it's a root 2 times root 5. And the only root 2 is here, so that's mine. So now this can't be a mine. And also root 5 is a knight's move away, so none of those are mines either. Now this 2 is a 1 times 2, so a root 2 is not a mine. The root 2 distance is not mine. This 1 is just 1 times 1, there's nothing else you can do with it, so these are both mines. And now this can't be a mine. This is the first use of connected after the first deduction, where if this was a mine, you would form a region that isn't a rectangle, so that fails. So this can't be a mine. Similarly, this can't be a mine because you have a region that is not a rectangle. And now root 2 is 1 times root 2. Well, this, whatever this is, has to come out here. There's nowhere else to go, so it has to come out here. That's your root 2, but you could have as many root 2s as you want besides this root 2, so guess not. Okay, what else is there? Probably mine count, or maybe mines here. Yeah, in fact mines here actually do have some problem, don't they? No, they don't. Mines here could just travel this way. So like I'm pretty sure like your group of 6 mines could look like this. I think that's fine because it's a 1 times a root 2. And you can have as many root 2s as you want. So that's not a problem. Maybe this? If this is a root, yes. If this is a mine, then this can't be a mine. Because if it was, then your number here would just be a 1. But if it can't be a mine, then it will just isolate this mine. So this can't be a mine. Cool. 1 is just this times this. And now this must escape. But can't take this because it will form a region that isn't a rectangle. This has to escape, so that happens. You can't form another one here, so this can't be a mine. And now this must escape. 2 mines remaining. Well, that's very interesting. The only way to make it 2 mines remaining is actually putting a mine here. It's almost like a Zugzwang if you don't, which is really cool. If there is no mine here, that actually fails. Even though you have more mines, which is supposed to help connect it, that actually fails. Because however you put the 2 mines, it's either going to be not connected like this, or it's going to give you a region that isn't a rectangle. Wow. So this has to be a mine. And then there can only be one mine left here and must connect everything. So that must be this one connecting cell. Oh, that's really cool actually, that final deduction. That final deduction is quite nice. Okay. I think we have one more to go. And I think we can afford one more. Time for one more puzzle. Probably we definitely can. Okay, encrypted and segment. So encrypted is, well, it's pretty obvious if you look at it. Every letter corresponds to a number. CBA. Oh my gosh. Isley would be proud. Isley would be so proud. That's crazy. I should stop doing that. Oh, what? Oh, this is okay. Hi. Come back. CBA. I'm just gonna... There you go. Sorry, so no distractions here. Basically, every letter corresponds to a number, and every of the same letter corresponds to the same number, so these two C's are the same number. In addition, segment means that every row must have only one consecutive segment of mines. So you can't have two different groups of mines together like this. You can also have 0 mines in the row. So yes. Alright, so those are the rules. C, we can clearly observe, I don't want to say C twice in a row, that it can never have a number bigger than 1. Because you can't have more than one mine in here. So what that means is that none of these are mines, and coding actually gives you that answer straight away. E can't be greater than 3. And we do know that every letter is a different number, and every number is a different letter. So you can't have two numbers. You can't have two letters give the same number, basically. Whatever C sees over here, this C would see that, so there will be no mines here. D can't be any greater than 2. B also can't be any greater than 2, which means that the only number that can be 4 is A. So A is just a 4. Okay. We know that B must see more than C, because whatever C observes, whatever C can see over here, B will see at least one more of it. And because it must see one more, it can't see the same number, this must be a mine. We also know B can't be 0, and that C, well, we already know C can't be 2, so there you go. We also know that whatever D sees, B will see more of it. So D can't be very big, it can't be 2. And in fact, because C and D are either 0 and 1, that sort of gives you an idea that nothing else can be 0 or 1. B must therefore be a 2, and E must therefore be a 3. Now this must be a mine, and therefore C is a 1. Cool. Alright, D is a 0. That gives you this. 2 can be completed. I think we're going to solve this like a regular Minesweeper puzzle now. 3 means all of those are mines. 4 means... Oh, segment. Right, I forgot segment was a thing. we just did encryption all the way. Anyway, segment is... Well, it's very helpful here where none of those can be mines. Oh, I almost lagged there. Anyway, 3 means those are all mines. 4 is not complete. There must be a mine here actually, because otherwise there will be 0 segments, which doesn't work. So that's a mine. 1 mine remaining, and it can't be in those cells, otherwise it will be separated from this mine, giving you segments, giving you multiple segments in that row. So mine must be here, and that solves it. Cool. And there you go. 10 5x5s gives you the 5x5 gallery, which is, yeah, a combination of everything. 2, 4, 6, 8, 10. And I think there is one more set of, yeah, G and E. Or is it, what? No. G and X, I think. G and X we haven't actually seen yet. But that's okay. We'll do it next time. Probably here. No, H and P. Okay, well, whatever it is, we'll do it eventually. We'll do that combination eventually, because I'm gonna have to fill up the box for every gallery size. So yeah. Alright. Well, this was fun. This was really fun. I can't wait to do End though. End seems pretty fun in itself. But until then, hope you enjoyed this video. I'll see you guys next time. Bye bye.